So you'll notice in your packet that you are going to use several types of spectroscopy to determine knowns, right? So we'll relate known compounds to the type of changes we'll see in spectroscopy, but you also have 10 unknowns in your packet. And so we want to talk about some strategies for determining the molecular formula of an organic compound from the mass spectrum, right? So we have a mass spectrum, we don't know what the compound is, and we're going to try to determine its molecular formula. Now, there are a couple different ways you can do this. This is particularly a new way for me to, the way that is outlined here is a new way for me. And we can talk about that more in class. But I do like this way. I do think it's very savvy. So this is a nice step-by-step process that's outlined here. And the very first thing you need to do is you need to assign the molecular ion peak. If it's not given, you need to find it, right? You need to look at the high end of the spectrum. Right? And look for two major peaks that are separated by 2U in their M to Z values, right? And if it's separated by 2U, then you're going to see, of course, an M+2. You can also look for an M+1 peak. If no M+2 peak is apparent, that M+1 peak is what you're going to see. Okay, you're going to see these peaks. So let's find those. We already know we can get some good information for that. The next thing you need to do is record the number of carbon atoms. So sometimes the number of carbon atoms will be given to you. If they're not given to you, you can estimate those intensities by plugging those in to that equation where it's M+1, right, intensity over that radical intensity times 100 over 1.1. And of course, these are all percents and they're all going to cancel out. And that's going to give us the number of carbons. And that's a really, really helpful piece of information. Then what we can look at is we can determine if the molecule contains any heteroatoms. Now, heteroatoms are just things other than carbon or hydrogen. And so a couple things you need to think about, right? You need to think about that nitrogen rule that we talked about. Okay. When we talk about the nitrogen rule, does that suggest the presence of any nitrogen atoms? Okay. Then, if there's an M+2 peak, right, is that going to be bromine or chlorine? Okay, those are the only two that we're going to see as far as our spectra are concerned. The next step is to compute the remaining mass. And the way you do this is you subtract the mass of the carbon atoms that you determined in step 2 and the mass of the heteroatoms that you determined in step 3 from the molar mass or the molecular weight. Okay. And then for step 5, you need to determine whether the hydrogen atoms can account for the remaining mass. If so, then you have a complete molecular formula that can be totally feasible, right? If not, then you need to think about other non-hydrogen atoms. So I'm going to put just here, if not, think about other heteroatoms, right? Like oxygen or fluorine, right? And then you can repeat that. Now, you may not get just one formula from your mass spec. You may get 2 or 3 options. That's why we're going to have other spectra that can give us clues into our structure and formula. So know that this is not the end all be all. You'll be able to get to a certain point and you'll be able to say, well, I know it's probably maybe one of these things. And then you'll have to look at other spectra. So this is just one piece of kind of this gigantic puzzle. So if you love puzzles, this is for you. So let's do some examples. So here's our first unknown. We don't know what it is. And we're going to determine the molecular formula. So we're not given the M+1 peak or the molecular ion peak, but we are given some abundances. A great context clue here is if you're given abundances, that's generally important information. So I look here and I say, okay, look, there's this peak here with a 30% abundance and this peak here with a 2.4% abundance, and they're separated by 1 mass here. So that means this is probably my molecular ion peak, right? And then this guy is my M+1 peak. Now I can look at that and assign some mass to charge ratios just by looking at the x-axis there. And so what we're going to see here is that molecular ion peak is going to have a mass to charge, it looks like it right there about 129, right? And it's got a 30% abundance. I just like to list everything. Okay, and then the M+1 peak, of course, its mass to charge is going to be one more, so that looks like it's at 130, and that's got a 2.4% abundance. Now, right, that gives us some great information. It tells us our molecular weight of this unknown compound is going to be about 129 grams per mole. So that's helpful off the top, just off the bat there. Let's figure out how many carbon atoms we have. So that was step 1. So let's look at step 2. Let's figure out how many carbon atoms we have. So we are going to put that M+1 intensity, 2.4%, right, divided by 30% times 100 over 1.1%. And again, that comes from the natural abundance of carbon. And when we do this, I got like 7.27, which I'm going to round up to 3. But make sure you're getting these numbers, that you're putting everything in your calculator correctly. So that tells me we're going to have about 7 carbons. Okay. The next step is we need to evaluate if we have any heteroatoms. So when we're looking at this particular step, the first thing we're going to do is the nitrogen rule. Okay. And so when we talk about that nitrogen rule, right? So with the nitrogen rule, if we have an odd number, odd molecular weight, it generally means we are going to have an odd number of nitrogens, right? So if we have a nitrogen, we are going to have an odd number. So if nitrogen, we will have an odd number. Now, the next part of step 3, when we're talking about heteroatoms, was to look at the M+2 peak. We don't have an M+2 peak here, so we can just ignore that part of the rule. It doesn't apply to this example. Now, let's go on to step 4. Now, when we look at step 4, and of course you can always refer back to your notes, we need to compute the remaining mass. So we have 129, that's our molecular weight, and I am going to subtract the mass of 7 carbon atoms. So the mass of 7 carbon atoms is 84, okay? And that leaves us with 45 atomic mass units, or 45 U, okay? Now, here's where we start to make some leaps, right? So that's due to carbon. Those particular 7 carbon atoms. And now we have kind of this idea that we could have a nitrogen since there's an odd number, but we're not really sure. We could have other heteroatoms. If we assume the compound contains 3 nitrogen atoms, if we're looking at atoms, that would give us 42, okay? Now, that's not very likely because we know that this has to include your hydrogen atoms, right? And hydrogen atoms have a molar mass of 1. So we're not exactly, so 3 nitrogens doesn't seem to be really likely because you wouldn't have enough molecular weight or molar mass left over to accommodate your hydrogens, okay? Now, It's more reasonable to assume that this would contain just one nitrogen atom. Okay, so this is where we kind of get into some areas where we're making some assumptions, right? And this is where having other spectra is really helpful because, for example, next week when we learn IR can help you narrow down whether, or give some clues onto whether you would have a nitrogen. But we're going to assume we would have one nitrogen atom. Okay. Now, if we have one nitrogen atom, okay, so 45 is what's left over, right, minus our one nitrogen atom, which is 14, that gives us 31 atomic mass units that aren't necessarily accountable for. So that's like C7N. It would be really unlikely that we would have 31 hydrogens with that. That's just weird, considering that when we think about, you know, CN, H2N plus 2, right? If you have C7, it'd be H1416. So 31, there's no molecule that's going to have that. So that indicates that we are probably going to have some other heteroatom. Okay, so probably another heteroatom. Okay, so we know we're going to have we have this idea that we're going to kind of have one nitrogen. We're not going to have two nitrogens because it's not an even molar mass. And so we can conclude probably that this guy here is going to be some sort of oxygen or fluorine. Okay, so good educated guesses here would be we'd have C7, H15 with the nitrogen and the oxygen. Now this may be a really good time to go back and to review some of those saturation equations that we did in the first semester, right, with the IDH numbers, because you can see where we've gone back and, you know, taken out, it's not if it was saturated, right, we've taken out some of these hydrogens, or maybe C12NF, right? So there's a couple different things we can be. We could see that these add up to 129. So these would be some good educated guesses, but that's it. That's all we can figure out from mass spectrometry. That's why we have to have other tools, other spectra to help us identify what the final compound is. So we get a lot of clues here, but it doesn't tell us anything about the connectivity, really. So that's why we have to learn about other spectroscopy methods. Let's do one more. So here's unknown 2. There's the mass spectra. It says propose a molecular formula for this compound. We are going to go through our steps, right? And so when we go through our steps, the first question, of course, is just for that step 1, are there 2 significant peaks separated by 2 atomic units at the high mass end of the spectrum? Now, if you look at the next 2 slides, I have places for you to fill in this information just because I like tables. If I skip ahead, it will make the screencast break up. So I'm not going to skip ahead to that, but I do want to point you to the next 2 slides. So when we look at this, what we see here, first off, which is lovely, is they're giving us some big hints here. They're giving us those percentages, okay? And that's always going to say, well, that means it's probably something that we need to use. And so what we see here is there are 2 kind of biggish peaks here on the high end of the spectrum that are separated by 2 mass units. So first off, out of the gate, this indicates that we're going to have a chlorine or bromine. If I look here, I can already tell those are about 50-50. So that indicates to me it's going to be a bromine, right? Just from nothing else. So let's record some of this information, which is really helpful. So on that step 1, right, it says, are there 2 significant peaks separated by 2 atomic mass units at the high end mass of the spectrum? Why, yes, there are, right? We have a mass to charge ratio there of about 150, right? And Then we have that M to Z that's right around 152, okay? And so what we can do then is we can identify this as the molecular ion peak, right, as 150. That means my molecular weight of this compound is going to be right around 150 grams per mole. So very helpful right out of the gate. Now, we have some abundances because we also have an M+1 peak. I didn't label that as my M+2. We also have an M+1 peak. That's right there at 151, and we do have the abundance of that. That's 0.7%. Okay, so we are going to figure out in step 2 how many carbon atoms there are. So we're going to take that molecular ion abundance. We are going to divide it by the abundance of just our molecular ion peak, which is given here. It's 14.7%. Multiply it by 100% divided by 1.1%. And that gives us 4.3. So we're going to estimate here that this unknown has 4 carbons. So we're going to do a therefore 4 carbons. Okay. So let's jump back down to step 3. So does this guy have an odd or even mass? So this has an even mass. And so we have some options here. We're either going to have no nitrogens or an even number. Okay. Now, the M+2 and the molecular ion peak have about the same intensities. And so that indicates a bromine atom. Okay, so we're pretty sure this sucker's got a bromine in it. So what mass remains after we account for the atoms in steps 2 and 3? And so that leads us to step 4. So 4 carbons would give us a molar mass of 48U, right? 12 times 4 is 48. And bromine, like if we had 79 bromine, that would give us a molar mass of 79U. So if we have our molar mass of 150, which we get from that molecular ion peak, and we subtract 48, and then we subtract 79, that gives us 23 units that are left over, okay? So nitrogen can't account for the remaining mass, okay, because you can only have even. So if you had 2 times 14, that would give us 28, which is more than the 23. So that doesn't work, okay? So we're not going to have a nitrogen, so we can rule out nitrogen here. So the question here with step 5, right, is can the remaining mass be accounted for with just hydrogen atoms? Okay, well, so when we think about this, if we have a saturated carbon compound, carbon 4 and then H2N plus 2, that would give us carbon 4 H10. And even if that was completely saturated, that is much smaller than that 23 there. So we probably are going to have some other heteroatom in there. So this is where you need to kind of start seeing, right, what are some possible molecular formulas with either oxygen or fluorine that could add up to 150. And so some good options would be things like C4H7BrO, right? Or C4H4BrF. And this is where there's a little bit of trial and error because this is all we have. We don't have any of the other spectra to kind of help us with this trial and error. These are great methods to use. I really highly suggest that. Like all things in chemistry, practice is going to help. So make sure we're doing some practice problems.